This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
So, good morning and welcome back to the WE-Heraeus International Winter School on Gravity and Light. The topic of today's tutorial is diagrams, and as most of the times we want to start with today very short statements, but nevertheless 5 statements on the Schwarzschild black hole. In Schwarzschild coordinates, null geodesics starting at r larger than 2m never reach r smaller than 2m. That's correct, because when you remember the space-time diagram where we draw the radial and the time coordinate here, then we had the singularity at 2m, and this point is excluded, so starting out of here can never end somewhere here. The exact form of the null geodesics is like that and like that. These are the ingoing ones, and here this is the part for the region r smaller than 2m, so here we can't jump over. Next one. A Schwarzschild black hole is a non-rotating but charged black hole. That's not correct, since that's the Reisner-Nordström solution. If we cross out charged, then this would be correct, but as it is phrased here, it is not. In Eddington-Finkelstein coordinates, radial null geodesics fall into the black hole on straight lines at angle 45 degrees. That's right. If you remember the diagram that was constructed in the lecture, so here we had r again and the time, here was again 2m, then these here became that ones. So that's right. Eddington-Finkelstein coordinates cover all possible radii are in 0 to infinity. As you can see, that's right as well. Null geodesics in Schwarzschild coordinates starting from r smaller than 2m can never leave this region. That's true. Again, same argument as above. The point 2m is excluded, therefore you can't pass this point. And that's it. We continue with exercise 2, null geodesics. Conformal transformations of the metric have no effect on the geodesic equation. The question here is that we should show that a curve gamma that is a null geodesic with respect to a metric G, if and only if it is a null geodesic with respect to omega squared times G, where omega squared is a smooth function on M that is nowhere vanishing. Okay, so what we need to check is if we, for example, start here, what does that mean? We have a connection with respect to the metric G, and x is now the tangent vector to the curve gamma, then gamma is a null geodesic. And what we want to check here is whether, if we use this condition, this one, omega squared G, the other connection, xx, is again a null geodesic. That's what's to show here, and just to comment on that, that would be only the one direction, but the other follows immediately because you just need to invert this factor here and then that's the same. So we will just do the one direction here. Okay, and what we want to look at is the 8th component of this thing, and as you know, this is xa d by dxa. Sorry, this should be some b, otherwise we get an index conflict, and this acts on xa. So that's the first term of the covariant derivative, and now we get the gammas, but we need to be careful. These are the gammas with respect to the new metric, the conformal transformed metric, as we say. Then the A goes here, we derived with respect to B, and we maybe put some n here, so we have x, b, x, n. That should be correct. Okay, we continue by just leaving this term here, and we have to write out the gammas in order to see what happens here. So the definition was 1/2. Now we get the inverse metric in front, but in order for this to be the inverse we need the factor 1 over omega squared. Then here's the metric, and we choose indices a, d, for example. Again, we leave out the -1 that should be here, but you know what that means. And then inside of here we have the metric, which is nabla squared g, omega squared g. Then we have the indices n, d, b plus omega squared g, and now we have d, b, n. That's the next one, minus omega squared g, and here we have nb, and here it is d. So we check, we need nb down here, the 1 is replaced by the summation here, and we derive with our symbol. So this comma again means d by dxb, here d by dxn, d by dxd. Okay, that should be correct. And now we have a close look at this term. So here, here and here we will get some product rule. That means we have 6 terms in total. 3 of them will just reproduce the old gammas, because this omega squared factor stays untouched in front of each of them and cancels with this 1 over omega squared. So what we can write is d by dxb xa plus 1/2. No, I wanted to do this faster. So we saw that this produces the old gammas, therefore this is g gamma. Up we have an a, and down nb on xb xn, and I realized that here xb xn was missing, otherwise we would have some index problems. So these are the old gammas, and now we have to carefully look at the other part. So what do we have here? We have 1/2 in front, 1 over omega squared, then the inverse metric, this stays untouched, and now the bracket opens, and now this derivative acts on the omega. That means the g stays untouched like that, and now we get 2 omega times omega b, and the same for the other terms. That means g db twice omega times omega n. I continue here, minus the g nb now times 2 omega times omega d, and don't forget the xb xn. So that's it up to here, and now we again analyze what we have here. This one is just nabla x connection with respect to the metric g x, and of that the 8th component, but we know that this is 0 because that was our starting point. So this one is gone. So in the right part we may have a closer look at the last term here, this is basically GNB xbxn. But GNB xbxn is just the length of the curve. And since we started from null geodesics, this one is gone as well. So what remains, we do some reordering. This 2 cancels this 2. Here one of the square goes. And what remains is 1 over omega GAD. In there it is G. And now we see that because of the sum here and the symmetry of the metric, we can write this also as 2 times G ND omega comma B. Now we have XB XN. That should be correct. Okay. So what's the next step? We can pull the 2 out. That means we stay with this one. And now I wanna, well, we could contract these 2 here. That means we sum over the D and get some Kronecker delta AN. Okay, and this AN takes this one and makes this one into an A. That means we have comma B, that one stays untouched. These produce the delta and this one gets some XA. Okay, that looks quite nice. One further step maybe, so we can also write this as twice the X acting on the logarithm of omega, and then this whole thing times XA, because the X acts as a derivative. That means 1 over omega is here, the 2 is there already, and then we need to derive the inner part, and this is just omega comma b if we expand the X in some sum over the b's. Okay, and now we carefully look at this term and maybe call it alpha. So what's left is alpha times XA. And if you look at this one, that's just a function, because that's a function. A vector field acting on a function produces a function. This is in total just a function on M. That means we can think of that as some parameter that scales the value. And if you remember, the most general form of the geodesic equation, that was this one. And only if we do some affine parameterization, this one goes. But it has not to go in order for X to be the tangent to some geodesic. And since we started up here with the left part of the geodesic equation and arrived at the right part of the geodesic equation, this is correct, and we showed that if we start from a null geodesic for this connection, then this conformal transformation doesn't change that. It changes the parameterization, but that doesn't matter because it's nevertheless a geodesic. And that's it. Okay, so in the third exercise we want to carefully construct the Penrose diagram of a radiation-filled universe. So we will guide you through all the necessary steps in order to produce the Penrose diagram for this situation. And the first step here is that we find the exact form of the radial null geodesics here. So first we read the question. Find a differential equation for radial null geodesics. So that is important. In a spatially flat FRW universe filled with radiation, we should use this chart and then write explicitly down the range of the chart variables. Okay, so the first thing that we notice is we are spatially flat. That means kappa equals 0. Our universe is filled with radiation, and if you remember, the scale factor was proportional to t to the 2 over n for all values of omega. That appears here. So this one basically comes from the equation of state, that is P equals rho times omega, and different omegas produce different matter types or radiation here. And for radiation we had omega equals 1 over 3. If we plug that in here, that means 3 times 4/3 produces a 4, and that means in our case we have t to the 1/2 as our scale factor. Okay, we only want to consider radial null geodesics, and that implies that theta dot and phi dot equals 0 in our case. And a very easy way to find this differential equation for the null geodesics is the following. So we know that the Lagrangian in a suitable parameterization is 0, or it is always 0 because these are null geodesics, that means the length is 0, and we can explicitly write out the Lagrangian. So this would be minus t dot squared plus t times r dot squared, and that's it. Because the metric for the flat case was just minus in the 0, 0 component and some a squared in the spatial part, and a squared is just t. So this is our Lagrangian, and we can do some reordering here. No, I want to start a little earlier. That means we put this to the other side and divide by r dot squared. That means we have t dot over r dot, the whole thing squared, and this is equal to t. Now we take the square root. That means we have t dot over r dot equals plus minus square root of t. And now we look at this expression, that is dt over d lambda, for example, if we call the parameter so. And now in the denominator r dot, but this is just d lambda over dr. And this, after application of the chain rule, is dt by dr. So we have this differential part of this equation. And since this is precisely what we want, because we want to draw a diagram TR, so we need t in dependence on r. That means this is the same as, now I will write the integrals at first, so this is 1 over square root of t, we divide by that, here it is dt equals integral plus minus dr. Okay, this can be solved. You get one integration constant because we integrate once, and on the left hand side we get twice square root of t, and on the right hand side we get c plus minus r. C is a constant. Now we can divide by 2 and square the whole expression, and we get t of r equals 1 over 4 c plus minus r squared. So that's... Oh, I see that we already solved what should be solved in the next question, but actually it doesn't matter, so we maybe put that here. So we should determine the t coordinate of this geodesic in terms of its r coordinate, and that's what we did already. But what we forget was the range of these two variables. So the t is in and the r is in. Okay, t should be greater than 0 and r as well. So this is our range here. We will, for each of the steps, explicitly write down the ranges of the coordinates because that's particularly important for constructing these diagrams. Okay, and I will put the form of the geodesics again here. So that's this one. And now we can draw a diagram in which we put sum of the geodesics, and by sum we mean we take the plus, we take the minus, and we shift by the c. So this essentially looks like that. So we have the r here, t is normally on the y-axis, and now we need to draw many parabola. So for example this one and that one, and of course they start over here, so we get this one as well, and we get this one, and like that it continues. But one thing that is important, since we specified these ranges here, this one and this one and this one and this one, they are not part of the diagram. So t is larger than 0. That means here these are really two different geodesics. So this is the first and this is the second one in that chart. That's how it looks. Okay, now we are asked to find some transformation, that is another chart, where these curves here are lines of constant slope plus minus 1. And that's always the second step, so we need to make the null geodesics that run on arbitrary curves to some curves that are like that or like that. And we will see how this works. And I want to rescale the t. That means we have some new t that of course may depend on t, r, theta and phi. And one way to find this one is to first solve this equation for r. So we do that. That would be r equals plus minus twice the square root of t minus c. See if this is correct. So times 4, and then we take the square root, we get 2 times the square root, and then plus minus because of that one, and minus c should be correct. And since we want all lines to be straight lines of constant slope plus minus 1, then it would be good to define this one as the new t bar. So t bar is now defined as twice square root of the old t. Okay, you could basically rescale the r coordinate as well, but that essentially doesn't matter. Okay, again we draw some diagram. Also it's not asked here, but it helps to understand what happens here. So now we have the r here and the t bar here, and now we get lines of constant slope plus 1 and straight lines of constant slope minus 1. And of course the c shifts them here, and we again look at the ranges. Of course the r stayed the same and the t bar also stayed the same since we just took the square root. Okay, so that's basically it for the first 3 questions here. One remark I have to make is that while we exclude t equals 0. That's important because this is our singularity, the Big Bang, so to say. And you can see that here actually, because we choose some particular dust model, or we choose some radiation model, this one, with omega equals 1 over 3. And if you look at the metric, this produces -1, t, and then it continues, and the t here, if this gets 0, then the metric would be degenerate. And this is what we usually call a singularity. So that's not good, and therefore we need to exclude the t equals 0, and that results in these points that are excluded. Yeah. And the last thing we could do is, these are the what's that? The ingoing ones, and these are the outgoing ones. Hope that's correct. Yes. So outgoing, ingoing. Okay. So that's it, and we continue with the next question because we are not done yet. Okay, let's continue with the next question, which is about the so-called null coordinates that we normally call u and v. And the idea here was, so the result from the last step was r and t bar, and we had the geodesics as curves of constant slope plus minus 1. And the idea here is now to cleverly rotate the coordinate system such that this is the u-axis and this is the v-axis. That means the null geodesics run parallel to the both axes. And we just define u as t bar plus r and v as t bar minus r. Okay, so if we do that, we arrive precisely at this situation, and we first look at the range. So t plus r, these are both positive, as we checked in the exercise before, or in the question before. So this is in 0 to infinity, and v is in minus infinity to infinity. Now we have to draw the diagram, and that means I want u on this axis, so here is u, that is v, and we can exclude this area. Maybe I have to do it somehow like that, otherwise you can't tell what that means. So u is larger than 0, and we know that the geodesics now look like that. So that's the first direction, and these are the others. But now we can further constrain this thing, because we can, for example, look at u plus v, which is twice t bar, which is of course greater than 0. And what that means is that we can also exclude this part here. Because here, for example, this point, we have u equals 2, for example, and v equals minus 3 or 4, and then this would be negative. So this is excluded. And similarly, we can look at u minus v, which is twice r, which is again greater than 0, and this condition will exclude that part. So we are left with this kind of wedge here, where u may run to infinity. But now we have all the null geodesics along the coordinate axis. And the reason to do this is because now we want to compactify this. That means we take some function that produces out of the infinity some finite value. And by doing that, this function that produces this cannot be linear. Therefore the cone structure would not be preserved if it would be like that. Because then, for example, a cone that first looks like that by this transformation could after that maybe look like that, which we don't want. Therefore we put the null geodesics on the coordinate axis, and then the rescaling just produces something like that. Okay, so we will do that, and one suitable function is the arctangent. So here we have pi half minus pi half, like that. And now this is, and that's also important, a strictly monotonous curve. So we define u, now capital U, that is the arctangent of the small u, and similarly for the v. And since this one is strictly monotonous, all the conditions that we had before now also hold for the capital U and small v, and capital V. So maybe first the ranges. So this u, you can check up here, was the small u was from 0 to infinity. That means the capital U is from 0 to pi half. And for the v we had minus infinity. That could be a possible value, so this is the range. But as I said, the conditions that u plus v must be greater than 0 and u minus v must be greater than 0 also hold. So we can draw a diagram that looks like this. We have u again here and v here. So this would be something like that, where here we have pi half, here we have pi half, and here we are at minus pi half, and all the other stuff is now not part of our diagram. And still the geodesics are either that or that. So we preserve the cone structure, which is this one, but compactified, or one would better say bounded our range of coordinates. So that was the second last step, and the final transformation that we have to do is again recover some, or a notion of temporal and radial coordinates, because the whole idea of this Penrose or Penrose-Carter diagram is to make some statements on the causal structure, and therefore we must preserve temporal and radial coordinates in the way that we are used to them. So we want to have some r here and some t here. So that's the aim, and then we can talk about future and past. Okay, and the final transformation basically undo these up here, but of course with the bounded new coordinates capital U and capital V. So we define r and t, where t is now u plus v and this is now u minus v. Okay? What we immediately see because of these conditions is that they both are larger than 0, which is good, because we want this to be some radial and some temporal coordinate. So we can write t starts at 0 and r also starts at 0, and in principle they can go up to pi, both of them. You can check. The u is at maximum pi half, the v as well, so this one is clear. And for the r coordinate it's the same, because we subtract minus pi half, that's adding pi half, and we have this range here that is in principle possible. So we draw the diagram that now is just this one. So we have the r here and the t there, and maybe put the pi. So that's it. and we basically could have everything that's in here, but of course there are more conditions. That is, for example, if we look at t plus r. What is that? This is twice u, just using the definition here, and we have seen that u is sorry, wrong way around. We saw that u is smaller than pi half, therefore twice u is smaller than pi. What that means is, adding these both up must be smaller than pi. This means we arrive here where this is excluded, so this is out, and since we kind of rotated back, the null geodesics again look like that or like that, and here at t equals 0 we have the singularity, our Big Bang. Okay, so that was basically constructing the Carter-Penrose diagram for a radiation-filled FRW universe that is spatially flat.